Addition is the most commonly used arithmetic operation and it is also the speed limiting element while making faster VLSI processors. As the demand for higher performance processors grows, there is a continuing need to improve the performance and functionality of arithmetic units like headers. In this video we see quickly the carry ripple propagation problem and we calculate the delay of the standard carry look-ahead header. So in the next video we see the Manchester carry chain, a logic to speed up the carry look-ahead header. High-speed headers include structures like the ripple carry headers RCA, carry look-ahead header CLA, carry skip headers, conditional sum headers, carry select headers and combination of these structures. Among these high-speed headers, carry look-ahead headers is much faster. In CLA headers, the carry delay can be improved by calculating each stage in parallel. I leave a link in the description about all these different kind of headers and I highly recommend you to look at the carry look-ahead header video, which can be considered a prequel for this video. The easiest and smallest header you can build is the ripple carry header, but it suffers for the carry propagation problem. In the example we had 11 plus 5 equals 16. This is a combinational circuit, so it doesn't have a clock and the circuit operates as soon as the addends and the carry in arrive. So immediately when the data in input arrive, the combinational logic starts to work and to change some logical levels, and after some time we have on the output a result. But this first result is wrong because we have to wait more time for the carry to propagate and allow the generation of the right result. So we need an extra time for S1 in respect to S0 because it has to wait the carry 1. And after another gate time we finally have the right S1. The same for S2 which has to wait C2 and so on till the carry out C4. So we have to wait more time for having the last sum and carry, so for having the right and stable result on the output. This time is called the delay of the adder, and it is the time the last bit needs in order to be stable. You see the delay is created by the carry propagation time. In order to face the carry propagation problem, we can use a carry look-ahead header. So let's see how the carry is produced. In the table, we see that when A and B are both high, we generate always a carry. So we can write that the carry out is A times B or A and B. Then we focus on this part here where we see that the carry out is produced when exclusively A or B is at 1. So when A XOR B is high and the carry in is high. So we can add this part of the equation. We call this part the generation part because if A and B is high, we always generate a carry out, and this other is the propagation part because it allows the propagation of the carry in. So we can write our equation in this way, and generalizing, we can write this. You can see that the carry out is calculating from the generation and propagation bits and from the previous carry. In a 4-bit header, we can write this equation from which is clear that even the last carry, the carry 4 in this case, can be calculated as soon as the 2 bytes to be added arrive, without waiting any carry propagation time, so all the carries are calculated in parallel, avoiding the propagation problem. This is the main idea behind the CLA. I strongly invite you to see my video about the carry look-ahead if this recap is not enough clear to you. Now, in order to implement these equations, we produce, as we've seen before, the propagation bit with an XOR gate and the generation bit with an AND gate. Moreover, to get the carries, the first and easiest way is putting an OR gate where there is a sum and an AND gate where there is a product. Implementing with OR and AND gates, we get the structure with 3 stages of gates. The first for the production of the generation and the propagation terms. The second is the AND gate stage and the third is the OR gate stage. So we have all our carries after 3 stages of gates, so 3 gate times. To get all CLA adder, we need another stage of XOR gates, so in the end we have 4 stages of logic gates. Increasing the number of bits doesn't increase the number of stages, which remain 4, but it does increases the number of inputs in the AND gates and the OR gates. Remembering that a logic gate is lower the more inputs it has, you usually prefer to stop the number of bits to 4, thus using blocks of 4 bits. In this example we had two 16-bit numbers using blocks of 4 bits. Using gates of 5 inputs is quite slow. To realize this, we see a 2 inputs OR gate in CMOS technology. It is composed by 6 transistors. A transistor can be seen as a switch that can be open or closed. We have 3 PMOS transistors and 3 NMOS transistors. The PMOS is a closed circuit when it has a 0 as input. The NMOS is a closed circuit when it has a logic 1 as input. The OR gate is derived by an OR gate plus an inverter. I leave links in the description about logic gates in CMOS technology and their delays. When the transistor acts as closed circuit, it can be represented by a resistor, so the OR gate can be represented by this circuit. The slowest path is when both A and B are at a logic 0. In this case, the PMOSes are closed circuits and the NMOSes are open circuits, so a current is created from the voltage VDD for charging this capacitor and a logic 1 appears here at the input of the inverter. The NMOS of the inverter is then a closed circuit and the output is at a logic 0, because this capacitor is discharged towards ground. To get the delay of this gate, for simplicity we assume all the resistances equal. So the total delay is given by the time we need to charge the first capacitor CL1 plus the time to charge the second capacitor CL2. This time can be expressed more or less as the resistances in the charging path times the capacitance to be charged, so 2R CL1. CL1 is the capacitance seen at this node and it is created by the capacitances associated with the 2NMOS plus that of the PMOS and that of the input of the inverter. Moreover, we have to add the time to switch the inverter, so plus RCL2, where CL2 is the capacitance of the output node created by the PMOS and NMOS of the inverter and by the input of the next gate. Now we want to simplify further and we say that all the capacitances are equal, so all the transistors have the same capacitance associated. So we assume all the transistors contribute with the same basic capacitance C. So in the first node we have connected 5 transistors, so a total capacitance of 5C. So the first contribution is 2R times 5C equals 10RC. The second contribution is R times 2C plus other 2C as input of the next gate equals 4RC. So the total delay of the OR gate is 14RC time in our very raw approximation. Things are more complicated than this, but this is just to give an idea. If we consider now a 5 inputs OR gate, we have the structure and the time can be calculated with the same assumption of the 2 input OR gate case, getting 5R times the capacitance associated with 8 transistors connected to this node. So 5R times 8C equals 40RC delay. The total delay considering also the inverter is now 44RC. You can see the more inputs a logic gate has, the slower it is. So a 2 inputs OR gate has 14 RC time delay and a 5 inputs OR gate has 44 RC time delay. We can apply the same method to the AND gate and get that the 2 inputs AND gate has 14 RC delay and the 5 inputs AND gate has 44 RC delay. But we need to know the delay of another gate, the XOR gate. The XOR is much more complicated than the AND and the OR gates and we simply call its time T-XOR. This time is longer than that of an AND or that of an OR gate but cannot be avoided, not even with the Manchester carry chain we'll see in the next video. Actually, the PMOS resistance is different from that of the NMOS. We could make them equal by making the PMOS larger, but we would add an impact on the capacitance shown by the PMOS. Moreover, the capacitances are not all equal, but we want just to give an idea and keep it simple. So now we are able to estimate better the 4-bit carry look-ahead at their delay. The first stage is composed by XOR and AND gates working in parallel to produce the propagation and generation bits. This stage takes the XOR time. The second stage is composed by AND gates working in parallel, and the slowest is the AND gate with 5 inputs, taking 44 RC time. The third stage is composed by OR gates working in parallel, and the slowest is the OR gate with 5 inputs, taking 44 RC time. If you remember the CLA header, there is a fourth stage with 2-bit input XOR gate working in parallel, so we add another T XOR time. The total time is then 2T XOR plus 88 RC. So now you can understand better why we stopped the carry look ahead logic to 4 bits. And in the next video we introduce the Manchester carry chain in order to replace the second and third stages with a faster logic. Please leave me a comment, let me know if you liked this video. Make sure you put a thumb up, click the notification bell and subscribe to my channel.